Hello everyone and welcome to our video on the unit circle. Alright, so the unit circle is basically a circle, well, it's a circle centered at 0, 0 with radius 1, but we use this tool, the unit circle, as a way of visualizing the sine and cosine functions. So we're going to start out by taking a look at the classic definition of the sine and cosine functions, and then we'll see how this definition extends to the unit circle, and then we'll figure out how to actually evaluate sine and cosine for various angles. Okay, so let's take a look. The classic definition of the sine and cosine functions is that for a right triangle with legs x and y, so x and y here, with hypotenuse r, as depicted in this triangle, sine and cosine are defined respectively as sine of theta equals y over r, and cosine of theta equals x over r. So you may have heard sine is opposite over hypotenuse, or cosine is adjacent over hypotenuse. That's an easy way to remember these things. But either way, we've got our angle theta here. This is y, this is r. Y divided by r is sine of theta, and cosine of theta is x divided by r. In other words, what the sine and cosine functions are telling us is the ratios of the sides to one another on those triangles. How do the lengths of the sides relate to each other? So it turns out that when we look at sine and cosine, these values are determined entirely by the angle, that base angle for the triangle. The size of the triangle is irrelevant, and we can see that in this diagram here. So here I've labeled S and C here, so maybe we'll go ahead and erase this. So, well, it's not going to erase. Oh, well, that's fine. No big deal. So we've labeled this S and C, and so here's what we want to see. When we look at our larger triangle with sides x, y, and r, right, we know that sine is y over r, and cosine is x over r. And when we look at this smaller triangle, what we see is that these are similar triangles. They have the same base angles, theta. They both have right angles. And if two of their angles are congruent, the third angle also has to be congruent. So since all three angles are the same, we call this small triangle here and the large triangle similar triangles. By definition, the ratios of similar triangles, the ratios of their corresponding sides are equal. Let me try saying that again. When we have similar triangles, that means immediately that the ratios of their corresponding sides are equal. So this is a fact from geometry. So when we look at this picture, what that tells us is that this side C divided by 1 will be equal to x divided by r, and the side S divided by 1 will be equal to y divided by r. And hence C equals x over r, which is cosine of theta, and S equals y over r, which is sine of theta. So what that is to say is that if I had a triangle whose hypotenuse was length 1, then sine and cosine would just be the legs of the triangle, right? I wouldn't need to take the ratios because I already know the hypotenuse is 1 here. So I can just say, well, then sine of theta is the vertical side and cosine of theta is the horizontal side. Okay, so that's going to lead us to a more modern and more powerful definition for sine and cosine. But first, we have to define what the unit circle actually is. And the definition of the unit circle is actually very simple. The unit circle is the circle with a radius 1 and its center at the origin, which in other words means it's the circle with equation x squared plus y squared equals 1. So again, unit circle is called the unit circle because its radius is 1 unit as opposed to multiple units. So if we take a look at the unit circle here, what do we see? If we take any point on the unit circle, we can draw a triangle, a right triangle, by drawing a vertical line down to the x-axis, right? and then drawing from the origin of the triangle to that point, that's going to form a right triangle with hypotenuse 1 and sides x and y, where x and y are the coordinates of that point on the unit circle. So, well, what does that mean? Well, that means that if I look at the unit circle, if I think of this as my theta, then my x is my cosine of theta and y is sine of theta. So I could also think of cosine of theta and y of theta as being the coordinates for the points on the unit circle. So that's how we're going to redefine these things. So the unit circle definition for sine and cosine: let theta be a central angle in standard position, and P of theta be the point xy on the unit circle that intersects the terminal side of that angle. So in other words, if I draw this angle theta here, and I draw my terminal side of my angle, right, this point xy is what we define as cosine of theta for x and sine of theta for y. So yeah, the whole point before was, hey, if I know that my hypotenuse has length 1 for my triangle, then I know that the x and y values of that triangle are just cosine and sine of theta. So I can extend this definition to this full circle, and now instead of only having sine and cosine values that relate to angles between 0 and 90 degrees, now we can extend the definition of these functions to any angle. So what we're going to start by doing is just looking at the three most basic angles. So we're going to talk more about this idea of reference angles specifically later on. We'll use that term occasionally here. But we start with these three reference angles that are between 0 and 90 degrees. So this is 45 degrees and 30 and 60 degrees. And so what we're going to do is take a look at how geometrically we can actually find the values for cosine and sine, which, remember, just means the values for x and y on these triangles with hypotenuse length 1. So let's start with the 45-degree triangle. So I know that all three angles of a triangle must add up to 180 degrees, and this is already 90, and this is 45. So that's 135 degrees. So what do I have left? I have another 45 degrees left. So that tells me that these two angles are congruent. And I recall from geometry that if my base angles are congruent, then that means the triangle is isosceles and the two sides are also congruent. So what I see here is that, oh, x and y are actually equal. So these are both x. So now instead of having two unknown variables to try to solve for, now I can reduce this to one variable, x. And since this is a right triangle, I can use the Pythagorean theorem to solve for that. So I can say, hey, x squared plus x squared equals 1 squared. Okay, well, x squared plus x squared is 2x squared. 1 squared is just 1. And now when I divide by 2, I get x squared equals 1/2. And so when I take the square root, I get x equals plus or minus the square root of 1/2. But negative here doesn't make sense because we're talking about the length of a side of a triangle. So we're just going to look at the positive root. And the square root of 1 is 1, so this is 1 over root 2. And now this is actually perfectly fine, but typically the way you'll see this written is rationalized. So I'm just going to multiply by the square root of 2 over the square root of 2. I'm really just multiplying by 1 here. And this gives me root 2 over 2. So the key thing here is that I got root 2 over 2 for x, but both of these sides are equal. So I also got root 2 over 2 for my y value. So when we go back to thinking of this as our trigonometric functions, what does this tell me? This tells me that cosine of 45 degrees is the square root of 2 over 2, and so is sine of 45 degrees. Okay, so that's one case down. That's the 45-degree case. Now, let's take a look at these next two triangles, and we'll deal with one at a time. First, we're going to deal with this 30-degree triangle. So if this angle is 30 degrees and this is 90, that makes 120. So what do I have left? That means this angle must be 60 degrees. Now, if I draw, now this is a clever trick, but nonetheless, this is the sort of secret here to geometrically figuring out x and y. If I draw a mirror image of this triangle, so imagine you're just taking this whole triangle and flipping it over and drawing a mirror of it. Well, what do we get? Well, this angle will also be 30 degrees. This angle will be 60 degrees. Again, it's a mirror image here. So that means this whole big angle is 60 degrees. And now, if I look at the large triangle here, right, so I'll just highlight this whole thing. This is a 60, 60, 60 triangle, meaning all three angles are equal. And if all three angles are equal, that means all three sides are equal. So we call this an equilateral triangle. Now the key here, though, is that since all three sides are equal, that means this whole side is equal to 1. Okay, well, what does that do for me? Oh, well, that means if the whole side is 1, y is just the top half. So that means y is 1/2. So now I figured out what y is. So now I have to ask myself, what's x? Okay, well, now since I know what y is, I only have one variable again. So now I can use the Pythagorean theorem to solve it. X squared plus 1/2 squared equals 1 squared. So x squared plus 1/4 equals 1. Subtract the 1/4, and I get x squared equals 3/4. Take the square root, get plus or minus the square root of 3/4. But again, we're talking about the length of a triangle's side here, so the negative answer doesn't make sense. So this is just positive root 3 over 2, since the square root of 4 is 2. In other words, what we can say here is that cosine of 30 degrees, right? This is my base angle, is 30 degrees. Cosine is the x value, is the square root of 3 over 2. And sine of 30 degrees is the y value, that's 1/2. Okay, so now we have one more case that we're considering here. We looked at 45-degree triangle, the 30-degree triangle. Now we're looking at the 60-degree triangle, and this seems like it's tricky, except that if this is 60 degrees, that means this angle is 30 degrees. So these two are actually the same triangle, just flipped around. So the geometry is exactly the same. That tells us x here is 1/2, and y is the square root of 3 over 2. And so cosine of 60 degrees is 1/2. And sine of 60 degrees is the square root of 3 over 2. Okay, so essentially what we've done is figured out all of the angles inside of the first quadrant that we typically write on our unit circle. Now keep in mind, I want to be really clear about something. The unit circle is just a circle with radius 1 centered at the origin. So there are infinitely many angles here, right? You can pick any angle you want, 12 degrees, 12.5 degrees, so forth and so on. But we only put angles, standard angles on the unit circle that are easy to evaluate geometrically. And that's what we've looked at here. These are just the angles where we can actually figure out what these values are using geometry. So if we take a look at the first quadrant of the unit circle, you'll often see it drawn like this. And what we figured out from our previous work is that for 30 degrees, the point on the unit circle, my cosine and sine value, is the square root of 3 over 2, 1/2. For 45 degrees, it's the square root of 2 over 2, square root of 2 over 2. And for 60 degrees, it's 1/2 square root of 3 over 2. Again, the x-coordinate is the cosine value, the y-coordinate is the sine value, and all we're looking here is at the two triangles that we saw before. When we have that 30-degree triangle, the short side, the y value is 1/2, right here, and the long side, the x value is square root of 3 over 2. And if we look at 45 degrees, that forms its own triangle here. And that triangle had sides square root of 2 over 2 for both sides, for cosine, the x value, and sine, the y value. And for the 60-degree case, it was the same thing as the 30-degree case, but flipped upwards. So now we have 1/2 for the cosine value and the square root of 3 over 2 for the sine value. Okay, so now we talked about this in terms of degrees so far, but as I've mentioned before, the further you move into calculus, the more you will use radian measure primarily when dealing with trigonometric functions. So that means that we need to be able to do all of these sorts of unit circle problems, whether we're using degrees or we're using radian measure. So I've redrawn these triangles that we were looking at before in terms of both degrees and radian measure. So our 45-degree triangle, that's the same thing as pi over 4. So if this angle is 45 degrees, what do we get across from 45 degrees? We get the square root of 2 over 2. Or in other words, across from pi over 4, we get the square root of 2 over 2. And when we look here at our other triangle, 30 degrees is the same thing as pi over 6, and 60 degrees is the same thing as pi over 3. So across from pi over 6 is 1/2. Across from 30 degrees is 1/2. And across from pi over 3 is the square root of 3 over 2. Across from 60 degrees is the square root of 3 over 2. So one of the things that students often try to do that is really not super productive is they try to memorize the entire circle of values that are labeled on a standard unit circle. This is not really an effective way to learn this, and it typically results in students doing things like spending 15 to 20 minutes at the start of an exam trying to redraw the unit circle. And that's like a really significant expenditure of time that actually isn't going to help at all. So instead, what we want to do is figure out how can we memorize the smallest amount of information possible and still know every value for sine and cosine that we need to know. And this is how we do it. By thinking of these two triangles, remember, whether it's in degrees or in radians, it's the same thing, right? So we really just have two triangles, and what we really just need to remember is that across from the angle pi over 4, we always get the square root of 2 over 2. Across from the angle pi over 6, we always get 1/2. And across from pi over 3, we always get the square root of 3 over 2. Likewise, across from 45 degrees, we always get the square root of 2 over 2. Across from 30 degrees, we get 1/2. Across from 60 degrees, we get the square root of 3 over 2. So I'm going to demonstrate how to use that rather than trying to memorize an entire unit circle diagram, which really isn't practical. Instead, we're going to just think about how can we use this idea, right, of just knowing these three pairs of values. Where does the 1/2 go? Where does the square root of 2 over 2 go? Where does the square root of 3 over 2 go? So that we can then picture all of our sine and cosine values across the whole circle. So let's take a look at our first example here. Find cosine of 135 degrees. And the way we're always going to start these is by drawing the angle in question. So I start with my initial side in the positive x-axis, and then I draw 135 degrees. Looks like this, 135 degrees. Now my goal is always to draw a triangle with the x-axis. So here's my triangle with the x-axis. And I'm trying to figure out what the side lengths of my triangle are, because that tells me the coordinates on the unit circle. So if this is 135 degrees, what's my little angle here? We call this the reference angle. This is 45 degrees, right? The whole thing is 180. 180 minus 135, that means the little angle is 45. And what do we know? Across from 45 degrees, we should always get the square root of 2 over 2. So that means when I go across this angle, I get the square root of 2 over 2. But I also know that this angle is 45 degrees, so this side is also the square root of 2 over 2. The difference is we're on the left side of the y-axis now, so my x values should be negative. And cosine is the x value. So cosine of 135 degrees is negative root 2 over 2. All I had to know to answer this question was that across from 45 degrees was the square root of 2 over 2. And of course, I also need to be able to draw my angles. As long as I can draw my angles and I know those three basic sets of values, 30, 45, and 60 degrees, or pi over 6, pi over 4, and pi over 3, then we're good. Now, I'll just add in the little extra information. What else do we know here? Sine of 135 degrees is positive root 2 over 2. All right, so let's do some more examples and keep applying this idea. So I've got a few more in degrees. We've got sine of 210 degrees. So 210 degrees, we have to think of this as 180 degrees plus 30 degrees, right? So I go 180 degrees, and then I go another 30. So I have to ask myself, what's the reference angle here? Well, I went 180, and then I went 30 more. So this reference angle is 30 degrees. And remember, we just look at these two different triangles. Across from 30 degrees is always 1/2, and then the other side will have to be the square root of 3 over 2. So across from 30 degrees is 1/2, and this side has to be the square root of 3 over 2, but we're in the third quadrant, so our y values are negative, and our x values are also negative. So here, sine of 210 degrees is just negative 1/2. And likewise, even though it wasn't actually what I asked, cosine of 210 degrees is negative root 3 over 2. So again, all I had to know here was that across from 30 degrees is 1/2, and the other side is square root of 3 over 2. Now, sine of 180 degrees, this is a special case here. So when we take a look at 180 degrees, this is just the straight angle. Now, this is important because I can't draw a triangle here. I can't draw a triangle with a straight line. Notice, right? The whole reason we could draw these triangles is because we ended up above the x-axis, and then we could drop a line down to the x-axis, or we ended up below the x-axis and we could draw the line up to the x-axis. But here, this is the straight line on the x-axis. So how do I figure out what sine of 180 degrees is? Well, you just have to remember that what we're talking about is a circle here. And it's not just any circle, it's the unit circle, meaning it has radius 1. So if this length is 1, and I'm going straight to the left, then the point I'm going to end up with is the x value negative 1 and the y value 0, right? So on the special cases, the quadrantal angles, either straight to the right, straight up, straight down, or straight to the left, straight down, whenever you do one of those angles, all you have to do is go, hey, I'm going either right 1, up 1, left 1, or down 1, and just draw the point. So remember, sine of 180 degrees, sine is the y value, so this is the 0 value here. Okay, so now we'll look at another example in degrees, and then we'll move on to doing examples in radians. So here we've got cosine of 300 degrees. So I'm going to draw 300 degrees, and I'm going to think of 300 degrees as being 60 less than 360. So I'm making almost a full circle, except I haven't gone a full 300 degrees. There's 60 degrees I haven't gone yet. So if I draw my triangle with the x-axis, right? I take my point and I draw up to the x-axis. And I look at this triangle, my reference angle is 60 degrees, and I know that across from 60 degrees, I have to get the square root of 3 over 2. And I know that my other side always has to be 1/2. If I've got the square root of 3 over 2, the other side has to be 1/2. And the y value here is negative because we're in the fourth quadrant. So the x value is positive, but the y value is negative. So now that tells me that cosine of 300 degrees is my x value. That's 1/2. Now, on the other hand, again, it wasn't asked, but I'll just go ahead and notice that this approach immediately gives me the sine value too. Sine is negative root 3 over 2. Okay, so now let's take a look at some of these in radian measure. So remember, in radian measure, we're just thinking about radians as portions of pi, right? So here I've got negative pi over 2. So if I draw my x and y axis, and I'm going negative pi over 2, so I'll just take negative pi and break it into two pieces. So I go here, this is my initial side, and I go down 1/2 of pi. That's negative pi over 2. Keep in mind, you can't draw a triangle with the x-axis here, right? Because the triangle you have to draw has to come from your endpoint and go straight up or down to the x-axis. Here, if I go straight up or down, I'm just on the same line. But that's okay, because if I'm going straight down, this is the unit circle, and my radius is length 1. So this point puts me at x is 0, y is negative 1. So sine of negative pi over 2 is negative 1. And likewise, cosine of negative pi over 2 is 0. Okay, now we have sine of pi over 6. So real quick, I'm just going to scroll back up here, and we're going to just copy these two reference triangles momentarily. Now your goal should be to memorize these. Just these relationships, right? Your relationship between your angle and your side. It's just 3 pairs of numbers. So this is the shortest, easiest way you could possibly memorize these things, by just relating it to 3 pairs of numbers. Okay, that did not copy properly at all. Okay, it does not want to let me copy that. Let's try that one more time. Okay, it's not going to work. We'll just redraw it real quick. All right. Sometimes Word is not very cooperative with me. So remember, we know that for pi over 6, the side across is 1/2. And for pi over 3, the side across is the square root of 3 over 2. And we know that for pi over 4, the side across is the square root of 2 over 2, right? That's what we found earlier. So we have 7 pi over 6 here. In order to draw this, I first need to break down 7 pi over 6. All right, that's 6 pi over 6 plus 1 pi over 6. But 6 pi over 6 is just pi. Again, I just looked for the biggest number that's divisible by 6 that's less than or equal to 7. All right, and then I split it up into the 2 parts that way. Okay, so now let's draw this. I've got pi plus pi over 6. So this little angle here, my reference angle, has to be pi over 6, because I went pi and then I went another pi over 6. So when I draw my triangle, my reference angle is pi over 6, and I know that across from pi over 6 is 1/2. And I know that my other side will have to be the square root of 3 over 2. And since I'm in the third quadrant, both of these values are negative. So that means that sine of 7 pi over 6 is negative 1/2. All right, next, cosine of negative 5 pi over 4. So notice this approach also avoids one of the other big time wastes of trying to convert back and forth between angles and radians. That's really unnecessary and complicates things a lot. Whereas if you're just remembering, hey, pi over 6 is across from 1/2, that's easy enough to remember. You don't have to do any conversions to degrees for that. Whereas if you're trying to memorize this whole big picture of the unit circle, odds are you'll have so much more on your plate that you're not going to take the time to do it once in terms of radians and once in terms of degrees. So with that being said, let's take a look at negative 5 pi over 4. Let's first split that up into negative 4 pi over 4 minus another pi over 4, which is negative pi minus pi over 4. So I'm going to draw my angle. My initial side is here. I should have been drawing my initial side before. I got a little complacent with that on that previous example. Okay, so here's my initial side for my angle. And now I need to draw negative pi minus pi over 4. So I go negative pi, that's negative the straight angle. And then I'm going to divide the next pi into 4 pieces. And I go negative one of those 4 pieces. So that means my reference angle here is pi over 4. And I know that across from the side pi over 4, I always get the square root of 2 over 2. And my other side will also be the square root of 2 over 2, except the x value is negative here. So cosine of negative 5 pi over 4 is negative root 2 over 2. And of course, the sine value would be positive root 2 over 2 for this one. Okay, and here's cosine of 0. Well, this is a nice and easy one because if I'm looking at cosine of 0, my initial side and my terminal side are the same thing. And I know that the length of the radius of the unit circle is 1, so this point is just 1, 0. And so cosine of 0 is 1, and sine of 0 is 0. So again, anytime you end up on one of these quadrantal points, you're just to the right, up, left, or down a distance of 1. So those points should be easy to figure out. And for any other points, any of these other standard unit circle values, you can just draw the angle and work from that. Okay. Now let's go ahead and extend this idea to the rest of the trigonometric functions. So again, on the unit circle, we defined sine as the y-coordinate on the unit circle. And we defined cosine as the x-coordinate on the unit circle. So the way we define our other functions is as follows. Tangent of theta is y divided by x. Cosecant of theta is 1 divided by y. Secant of theta is 1 divided by x. And cotangent of theta is x divided by y. And since sine of theta is y and cosine of theta is x, we can rewrite these definitions in terms of sine and cosine, which is, for many people, how you'll typically think of these other functions. So we call this the quotient identity for tangent. Tangent of theta is sine of theta divided by cosine of theta. And for cotangent, we also call that the quotient identity. Cotangent of theta is cosine of theta divided by sine of theta. For cosecant and secant, we call these the reciprocal identities. Cosecant of theta is 1 divided by sine of theta, and secant of theta is 1 divided by cosine of theta. So whether you choose to think of these as the values on the unit circle y over x, 1 over y, 1 over x, x over y respectively, or in terms of their relationship to sine and cosine. One way or another, you will have to memorize these. These are just the definitions of these functions, so you have to know what these functions are referring to, and there's no way around it. You got to memorize them. But you have sort of two choices, whichever version you prefer. I think that probably most people typically remember these in terms of sine and cosine, because quite often that's how you use them most frequently. Okay, so with that being said, we're going to continue to use the same approach now to evaluate cotangent of 3 pi over 4 over 4. But we're going to do it by first thinking of cotangent as cosine of 3 pi over 4 divided by sine of 3 pi over 4. So I'm going to start by drawing my angle. 3 pi over 4. So I'm going to break pi up into 4 pieces. And now I'll draw my initial side and go 1, 2, 3. That makes this my terminal side. And so my triangle has a reference angle of pi over 4. Right? I went 3 pi over 4 before, and I'm going all the way to pi, so what's left is pi over 4. And across from pi over 4 is the square root of 2 over 2. So both of these sides are the square root of 2 over 2, but my x value is negative here because I'm in the second quadrant. Okay, so cosine is 3 pi over 4 is negative root 2 over 2. And sine of 3 pi over 4 is positive root 2 over 2. So if I have a negative root 2 over 2 divided by positive root 2 over 2, that's just negative 1. I'm going to write my negative a little more clearly here. There. So cotangent of 3 pi over 4 is negative 1. Okay, and next we have secant of 5 pi over 3, and we want to think of secant of theta as 1 divided by cosine of theta. 1 divided by cosine of 5 pi over 3. So the same general approach here. Okay, first I look at 5 pi over 3, and that's the same thing as pi plus 2/3 of pi. Right? 3 pi over 3 plus 2 pi over 3, and 3 pi over 3 is just pi. So I start with my initial side. I draw my 1 pi, and I mark it. And now I divide my next pi into 3 pieces. And I count out 2/3, 2 of those 3 pieces. 1, 2. That makes this my terminal side. And so when I draw my triangle, what will my reference angle be? Well, this was pi, and this was 2/3 of pi. So what's left is another pi over 3. And across from pi over 3, I should get the square root of 3 over 2, and my other side should be 1/2. But this y value needs to be negative because we're in the fourth quadrant. Okay, so I need cosine, and cosine is the 1/2 value. So secant of 5 pi thirds is 1 over cosine of 5 pi thirds, which is 1 over 1/2. And 1 divided by 1/2 is 2. All right. So now we've done a whole bunch of examples of evaluating trig functions. And the thing I really want to emphasize up to this point is that we never looked at a unit circle diagram for any of these problems. And this really should be your goal. Now, the truth is, if you actually practice this skill, you won't have to draw these pictures because you'll be able to picture them in your head once you've practiced it enough. If you go through and draw each of these angles that are on the unit circle, practice drawing them, then when you hear 135 degrees, you should be able to picture that angle and go, oh, the triangle has negative root 2 over 2 for x and root 2 over 2 for y. And that will come with just a little bit of practice of going through and drawing these angles. And once you get that visualization, that will stick with you for a lifetime, as opposed to the rote memorization that usually will kind of fade away as soon as you're done practicing it continuously. So again, never once did we look at a unit circle diagram. That wasn't relevant here. All we had to know was these two triangles, right? Across from pi over 6 is 1/2, across from pi over 3 is root 3 over 2, and across from pi over 4 is the square root of 2 over 2. Now, with all that being said, we're going to just take a look at a couple other types of problems here related to the unit circle. Because remember, the unit circle is all of the points, not just the ones related to these special angles that we typically deal with. So here, we're going to ask a simple question. Is the point the square root of 11 over 6, 5/6 on the unit circle? Well, remember, the unit circle is the circle with equation x squared plus y squared equals 1. So if I want to check if this point is on the unit circle, all I have to do is plug it in to x squared plus y squared and see if we get 1. So let's check it. Get the square root of 11 over 6 squared plus the square root of, or plus 5/6 squared. And the square root of 11 squared is 11 over 6 squared, which is 36, plus 5 squared, which is 25, over 6 squared, which is 36. And 11 over 36 plus 25 over 36 is 36 over 36, which is 1. So yes, this satisfies the unit circle equation. So this point is on the unit circle. Okay, another one. Find all of the numbers u if they exist such that u, negative 1/4, is on the unit circle. So remember, these are x and y values, and they should satisfy that x squared plus y squared equals 1. So if I plug u and negative 1/4 into this equation, I get u squared plus a negative 1/4 squared equals 1. So u squared plus 1 over 16 equals 1. And so if I subtract 1/16, 1 minus 1/16 is 15 over 16. So I get u squared equals 15 over 16. And if I take the square root of both sides, I get u equals plus or minus the square root of 15 over 16, which is plus or minus the square root of 15 over 4. So those are the two possible values of u that would put this point on the unit circle. Okay, and example number 13. Find all of the numbers u if they exist such that u, 7/4, is on the unit circle. And I'm going to demonstrate two ways to think about this one. Because the first thing is that if we understand what the unit circle is, then the answer is actually really, really immediate here. So remember, the unit circle is a circle with radius 1. So one of the things we should ask ourselves is, what is the largest y value we can get? 1. What is the smallest y value we can get? Negative 1. It's a circle with radius 1. It can only go up 1 and down 1. So y has to be between negative 1 and 1. And likewise, x has to be between negative 1 and 1. So when I see this problem, find all the numbers u if they exist such that u 7/4 is on the unit circle, I can immediately say none exist because 7/4 is bigger than 1. And our y values have to be strictly between negative 1 and 1, or inclusive between negative 1 and 1, right? 7/4 is bigger than 1. That's not within this interval, so that's not possible. It can't be on the unit circle. Now, let's say you didn't think about that immediately and you just went ahead and started plugging into your unit circle equation. That would be okay. What would happen in that case? We would get u squared plus 7/4 squared equals 1. So u squared plus 49 over 16 equals 1. So u squared equals, now 1 is 16 over 16 minus 49 over 16. So we get u squared equals a negative 33 over 16. So we would get u equals plus or minus the square root of negative 33 over 16. But we can't take the square root of a negative number, so that's not possible. Now, this would be more work, of course, right? It's much quicker to realize, hey, 7/4 is bigger than 1. We can't have a y value bigger than 1 on the unit circle. We're done. But if we didn't think about that initially and we start plugging it into our equation, as soon as we get to this negative square root, we should go, oh, that's not a real number. So we're done. Okay, so let's go ahead and talk about one other thing here momentarily, which is the idea of arc length on this unit circle. So oftentimes you'll see problems phrased in a slightly different way than I've been talking about. I've been talking about the angles and evaluating sine and cosine and the other trig functions in terms of their angles. Now, what do we know about the unit circle? Because its radius is 1 and arc length equals the radius times the angle in radians, since the radius of the unit circle is 1, that tells us that the arc length, t, is actually equal to the angle theta on the unit circle, right? If the radius is 1, plug in 1 here, arc length, t, equals r times theta, right? If r is 1, then t equals theta. So what that means is that oftentimes you will actually see things talked about, trigonometric functions talked about as functions of the length moved on the unit circle. So in that case, you might hear things referred to this way. Each real number t corresponds to a point p of t equal to xy called the terminal point associated with t. And so in that case, you will see things like sine of t or cosine of t, but just keep in mind that that's actually the same thing as sine of theta and cosine of theta, along with all of our other trigonometric functions. There's no real difference. It's just a slightly different way of framing these things. But when it comes to evaluating the trig functions, we're really thinking about angles because we get those values from the triangles that we draw with those angles. Okay, so lastly, on this last page, on this last example, I should say, and then we have one more page where we're just going to look at a couple charts real quick. But this last example says the number of squirrels at a university is given by n of t equals 100 times cosine of pi over 2t plus 650, where t is measured in years and t equals 0 represents 2012. Find the squirrel population at the university in 2013, 2014, 2015. What is the maximum squirrel population and what is the minimum squirrel population? Okay, so A is pretty straightforward, but we have to figure out what t is. If t equals 0 is 2012, then 2013 will be t equals 1. So when we plug in 1, we get 100 times cosine of pi over 2 plus 650. And so if I draw the angle pi over 2, that puts me straight up here. And I know that the unit circle has radius 1, so I'm going straight up. That makes this the point 0, 1. And cosine is the x value. So this is 100 times 0 plus 650. And that's 0 plus 650, which is 650. Now for part B, 2014, that's going to be the second year after 2012. So when we go to evaluate n of 2, we get 100 times cosine of pi over 2 times 2 is just pi plus 650. And so now when we draw pi, that's our straight angle. That puts our terminal side here. And so our x value is -1 and the y value is 0. So this is 100 times -1 plus 650. That's 550. Okay, and now for c, we've got t equal to 3. So n of 3 here is 100 times cosine of pi over 2 times 3 is just 3 pi over 2 plus 650. And I'm going to do the same thing, right? I'm just going to draw my angle, 3 pi over 2. 3 pi over 2 puts me at pi plus half of pi. That puts me down here. And so this point is x is 0, y is -1. But we're asking for the cosine value, so that's 0. So this is 100 times 0 plus 650. So we're back up to 650. Okay, and so now part D, what is the maximum squirrel population? Well, notice that the bigger cosine is, the bigger the population is, right? Because we've got a positive number times cosine. So the larger the value of cosine, the larger the value of the population. And the maximum value for cosine is just 1, right? It doesn't matter what the angle is. It doesn't matter that I call it pi over 2t or anything like that. The maximum value for cosine is 1 because that's the biggest x value on the unit circle. So the maximum value, how do I want to denote? Let's just call this max of nt is just what I get when cosine was its biggest value, which was 1. So this is 100 times 1 plus 650, which is 750. And similarly, the smaller cosine is, the smaller my number of squirrels will be. So if I ask what the minimum squirrel population is, well, the minimum is just what I'm going to get when cosine is at its smallest value here. And the smallest number cosine can be is -1. So that's 550 total. Okay, so that's it for that problem. Now, we're just going to take a look at 2 charts real quick. So this first one is just about the symmetry of the unit circle. Now the thing is, the way we've approached evaluating the unit circle, the symmetry is kind of obviously built in, because when I'm looking at the unit circle as triangles, I see, oh, if I draw this triangle here and I draw its mirror image, of course they're symmetric. Of course they have the same y values and the x values are just negatives of one another. But here we're just laying that out explicitly. If you have a point xy on the circle, then you will also have the negative xy point. And you also have the negative x negative y point. And you also have the x negative y point. And you will also have the point when you flip x and y, so the point yx. So all of those points will also be on the unit circle. That's all this says. Now finally, I've included for reference the complete unit circle diagram here. But I want to be really clear, if you are trying to actually learn to evaluate trigonometric functions in a useful way, staring at this picture isn't going to do any good. And that's a mistake I see students make all the time. They think, if I just look at this picture, I'll know the trig functions. But you won't, right? That's just not how it works. You're not going to rote memorize all of these values. There's a ton of values on here. So what you can use this for is a quick reference to see if you got a problem right. But if you're trying to rely on redrawing this from memory on a test, either it's going to take you a ton of time and make it very hard for you to spend the amount of time you should on the rest of your test material, or you're going to make mistakes when you try to reproduce it because there's so much information to reproduce. It's much easier to do what we did before, which is instead of memorizing all of these values, to just remember 3. Across from pi over 4 is root 2 over 2, across from pi over 6 is 1/2, and across from pi over 3 is root 3 over 2. If you can do that, and you can draw your angles, then you know the whole unit circle already. And that's why we did everything in this section before we ever looked at this diagram, right? This diagram is, to be honest, not a student's friend, right? Again, I'm including it for reference so students don't think I'm intentionally hiding the unit circle diagram from them. Of course, that's not the case, but it's not actually your friend, and it won't help you learn this stuff. Just stick to thinking about those 2 basic triangles and how when you draw your angles, you can picture one of those triangles in that position. All right, well, that's it for this talk on the unit circle. Thank you for sticking around.